Unit 3, Video Lecture 5, Part 2, Electron Configurations and Noble Gas Configurations. Before we go on, which principle tells us that no two electrons can have the same set of 4 quantum numbers? That should be the Pauli exclusion principle. And which letter is pointing to the sublevel? Letter B.
The first energy level is really small. It hardly has room for electrons at all. An S sublevel is all there is. 2 electrons that constantly whiz. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. A little bit larger the second shell, 2 sublevels there in do 12. An S sublevel that maxes at 2 and a 6 for a P, if that's okay with you. It's okay with me. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. The third shell is even larger still, an S and a P top the bill. D sublevel is added on top, 10 electrons can fit at a pop. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. The fourth shell is the largest yet, S and a P and a D, I'll bet. An F sublevel is also seen. How many electrons? Up to 14. 14, that's a lot! 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Electrons are found outside the nucleus. They zip around in energy levels, which are made up of sublevels, which can then be broken down into orbitals, and 2 electrons per orbital. Each one has opposite spin. Woo, 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 woo. And it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Why does 4s fill up before 3d? Don't know. Because the force is enormous, you see. Overlap 4s has less energy than the supposedly lower 3d. 3d, I love seeing in 3d. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. The overlaps increase in frequency. 4f fills up way after 5p. That's weird. Keep track of the overlaps really cool. Oh, you just gotta use the diagonal rule. I love the diagonal rule. And 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. I can't wait, just tell me when. Get them all up, let's start again. Once up level fills and the next can start. Electron config is something that I heart. Oh yeah. And now it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Okay, you can stop now. Wait, oh my gosh, his face is turning red. Oh, thank goodness, that's over.
So, the diagonal rule is a memory device that helps us remember the order in filling orbitals from lowest energy to highest energy. The diagonal rule helps us follow the Aufbau principle. In order to follow the diagonal rule, we first write the 7 energy levels from top to bottom. We then put the sublevels that are present in each of the energy levels. Remember, energy level 1 has 1 sublevel. Energy level 2 has 2, the S and the P. Energy level 3 has 3, the S, P, and D. 4 has 4, 5 has 5, 6 has 6, 7 has 7. We then write arrows starting in the top right to the bottom left. So the first thing that we fill is the 1s sublevel, followed by the 2s sublevel, After 2s is filled, we come back to the top right and draw a line from 2p to 3s, and then draw our next line from the top right going to 3p to 4s. So notice, we're going to fill, following our order, after 3s, we come back to the top and fill 3p and 4s before coming back and filling 3d. So helping follow the diagonal rule is going to help you keep track of those overlaps. So let's practice a couple electron configurations. Hydrogen. Hydrogen has one electron. So according to our diagonal rule, we start here, and the first thing that we move through is 1s. So we can be done here. That one electron has a home in 1s. Now lithium. Lithium has 3 electrons. So I fill 1s first. And now I need to find a home for one more electron. So I come back up here and cross through 2s. Notice 2 and the 1, 3, which is my total number of electrons. Now nitrogen. Nitrogen has 7 electrons. So I start at 1s. So 1s2. I come back up and go through 2s. So I've placed 4 electrons so far. I need 3 more. As I travel through 2p, 2p maxes at 6, so there's more than enough room for my 3. That gives me my 7 total electrons. Neon has 10 electrons. So I start with 1s and go through 2s. I come back down to 2p and 3s. I come back down my next line, and p can hold up to 6. So now I have 2 and 2 is 4. I've got 6 here. That's my total of 10 electrons. Pause the video lecture and do the electron configurations for potassium, zinc, and lead. Now, when we look at the periodic table, the different blocks on the periodic table refer to sublevels. So this first set of 2 elements, this first 2 columns here are what's known as the S sublevel. When we look at this middle block, this is the P block over here, because any element ending in this section, the last part of their electron configuration is going to be P. The middle block is the D block, so anything here is going to be ending in a D, and the F block, which falls right in between here, is the F block. Now remember, the S sublevel can hold 2 electrons, and there's only 2 elements in each part of the S sublevel. The P can hold a maximum of 6, and there's 1, 2, 3, 4, 5, 6 elements there. The D can hold 10, 5, 6, 7, 8, 9, 10. D can hold 10, and then there's going to be 14 elements down in this F block. We can abbreviate long configurations by using shorthand notation or noble gas configuration. We're often concerned only about the outermost electrons, the electrons in the outermost energy level, called the valence electrons. So we can skip to places that we know are completely full and finish the configurations. Step 1 is to find the closest noble gas to the atom without going over the total number of electrons in the atom. We put that noble gas in brackets. We find where to resume the configuration by finding the next energy level, and we resume until the configuration is finished. So if we look at chlorine, chlorine has 17 electrons, so its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. This 2 and 2 is 4, plus 6 is 10, 12 plus 5 equals our 17 electrons. So here's chlorine, element number 17, which means the two noble gases are neon or argon. Well, argon has 18 electrons, so it has too many. So what we're going to do is we're going to select neon and put neon in the bracket. Neon is at the end of energy level 2. Remember this is energy level 1, this is energy level 2, and neon is at the end of energy level 2. The next energy level is 3, so we will continue our configuration at 3. The first thing we fill is 3s, and there's element number 1, element number 2, meaning that we have 3s2. Here we're in 3p, and chlorine is the 1, 2, 3, 4, fifth element, so 3p5. So in our longhand notation, this part of the configuration, this 1s2, 2s2, 2p6, is replaced by writing Ne. If we take a look at potassium, potassium is element number 19. The closest elements are argon and krypton. The krypton has 36 electrons, way more than the 19 of potassium. So that means that argon is going to be our noble gas in brackets. Argon takes care of 18 electrons. Potassium has 19 electrons. So we only need to find a home for one more. Argon's at the end of energy level 3. So the next thing we fill is 4s. And that 4s can have allows for 1 electron. Now bromine. Bromine is element 35, so we're going to look again at argon or krypton. Well, krypton has 36 electrons, more than bromine's 35. So argon will go in parentheses. This is the 4s sublevel, and there's 2 electrons there. And remember, according to the diagonal rule, this section of the periodic table is 3D. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 3D10. And bromine is 1, 2, 3, 4. Fifth element in the 4p sublevel. Pause the video lecture and do the noble gas configuration for these elements.